Hi guys, let's do binary tree right side view. So we're given the root of a binary tree and they say imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. So if we take a look at the examples, in example 1 they give us this tree and they want us to output 1, 3, 4 because if you're standing on the right side of the tree looking this way, you're going to see nodes 1, 3, and 4. In example 2, we're given this tree and we output 1, 3, 4, 5. So basically it's just the rightmost nodes in each level of the tree. Because this 2 has a 3 that's further to the right that's in the same level. But like 1, 4, and 5 don't. So we would put these ones instead. And then in example 3, let's just take a look at this because it's easier to see. So we're given this tree and then we output 1, 3 because these are the rightmost nodes in each level. In example 4, we're given an empty tree, so we just return an empty list. So in this one, basically we're going to want to explore the tree level by level. So we know it's going to be a BFS. And then on each level, we just want to add the rightmost node for each level into a list and then return that list. Or I guess the value of the node rather than the node itself. But yeah, same idea. And then, okay, so we'll start with our base case. So base case is if we are given an empty tree, we're just going to return an empty list. So let's just start with that. If root is null, return new array list. So we're just going to return an empty list. Okay, and then if it's not an empty tree, then let's set up our list to store our resulting values. And then we're also going to set up a queue of tree nodes for our BFS. And then we're going to add the root into our queue. So, because we need to start with the root in order to be able to explore the rest of the tree. So, while our queue is not empty, let's explore each level. So we're going to say int nodes in level is the size of the queue. So let's walk through an example as we do this. So currently our queue looks like this because we only added the root into our queue. Our list, we'll just say result because that's what we named it, is empty currently. And nodes in level is currently 1 because we have one node in the queue, which is just the root. Okay, and I'm just using example 1 to show you guys, but you could use whatever you want. You could use example 2 or whatever. Okay, and then, okay, so we're going to do a for loop. So for each node in our current level, which in this case is just 1, but like later we're going to have more. So for I is 0, I is less than nodes in level, I plus plus. Then we want to remove the top node, okay? And then check if that is the rightmost node, which we're going to know if it's the rightmost node because we're keeping track of how many nodes are in each level. So it's going to be that minus 1 because I is 0 indexed. So we're going to check if I is the number of nodes in each level minus 1 because we're iterating through I times. I hope that makes sense. But so let's remove the top node, which is 1. So then once we remove that, that's gone. But we're storing it in this variable node. And then we're going to check if I is nodes in level minus 1. That means it is the last node in the level. And we're going to add that to our result, the node's value. So in this case, this is true right now because we have one node in our current level, I is 0, and then 1 which is nodes in level, minus 1 is 0. So I equals 0, and we are on the 0th iteration, which is true for this case. So we're going to add that to the result, and now our result looks like this. Okay, and then we're going to want to add the nodes children into the queue, because that's going to be the nodes in the next level. So, but we only want to do that if it's not null, because if it's null, like if we're at node 2, for example, and then we check node.left, that's null. So we're not going to want to add anything for that. So we're going to just do a check if it's null. So if node.left is not null, queue, dot add node.left, and then we'll do the same thing for the right node. And then at the end, we will return the result. But let's still walk through the rest of this. So we left off here. So we add the left and right nodes of our current node into the queue. So we're going to add 2 and 3, right? Because 2 is node.left, 3 is node.right, and neither are null, so we'll add both. And then we are back up here. So the nodes in current level are 2, so this is 2. And then we're going to loop through 2 times, basically, 0 and 1, for I mean. And then our top node is going to be 2, and we removed it, so let's take that off. And then if I is nodes in level, so nodes in level is 2 minus 1 gives us 1. I is not 1 because we're at I equals 0 currently, so we're not going to do anything here. And then node.left is null, so we're going to skip this. And then node.right is not null, so we're going to add node.right into the queue, which is 5. And then we still need to loop through again, because so now we're at I equals 1. And then we will, so we're going to pop off this node, which is 3. And we're going to store that into this node called node. And then nodes in level was 2. So 2 minus 1 is 1, and then we are at I equals 1. So we're going to add our node's value, which is 3, into our result. So 3. And then continuing on, node.left for 3 is null, so we're not going to add anything here. Node.right for node 3 is 4. So we're going to, which is not null, so we're going to add 4 into the queue. Then we loop back around up here. Nodes in level is 2, because we have 2, we have 2 nodes in our queue. What is going on, guys? Sorry. We have 2 nodes in our queue here, so that's still 2. And then, so we're going to loop through the for loop 2 times again. And so this is I equals 0 currently, and our node, so we're going to remove the top node, which is 5. So let's remove that, but we store it in here. And then nodes in level is 2 here, right, as we can see. And we have that stored here. So 2 minus 1 is 1, but we're currently at I equals 0, so this is not true, so we're going to skip that. And then node.left for node 5 is null, so we're skipping that. Node.right for node 5 is null, so we skip that. And then we're back at the beginning of this loop, and I is 1 now. Then we pop the next node off of the queue, which is 4, and store that in this node called node. And then nodes in level is 2. 2 minus 1 is 1. And we are at I minus 1, so this is true. So we will add our current node's value of 4 into our result. And then node.left for 4 is null, as you can see. Node.right for node 4 is null, as you can see. So we skip both of these. And then we loop back. And our queue is empty. God, I don't know what is up with this thing today. We are done because our queue is empty, so we will just exit out of the while loop, and then we'll return result, which is 1, 3, 4, which is exactly what we have here. So let's run this. Okay, and then our time complexity is O of n, where n is the number of nodes in our tree. And so first, let's just think about this conceptually, right? So we are doing a BFS where we visit every single node level by level. So because we're visiting every single node, that's going to be O of n anyway. We have this while loop where we are adding and removing, and a for loop. But basically, the while loop and for loop are not like n squared or anything, because the while loop is kind of going like up to down, and then the for loop is like nodes in each just level by level. So it's never gonna be like O of n for like just one level, you know what I mean? Like combined they're O of n. I don't know if that makes sense, but basically you just need to know that like we're just visiting every single node once, which is why it's O of n. And then space complexity is, so O of, this is kind of weird, but like I guess O of w, or we could say like O of n, I guess. No, I would say like O of w, where w is the maximum width of the tree, which in a complete binary tree is n over 2. So I guess that's why you could say O of n, because that would simplify to O of n. Or you could say O of w, where w is the maximum width of the tree. But it's because worst case, the max, like, or not worst case, but like if it's a complete binary tree, like perfectly bushy or whatever it's called, you're gonna have n squared nodes in the very last row, which then you're gonna have to store all n over 2 of those nodes into your queue, which is why we have that space complexity. And then n over 2 would simplify to O of n, so that's why I said O of n. But I think either of these is correct. So yeah, but I guess best case for space also, like if you just have like a straight line, like case 3, then it's just gonna be O of 1, because then of course they don't show it now, but because every single iteration in the loop, like you're only adding one node at a time into the queue, if that's the case. But that's also like a edge case, like that's not very common. So yeah, and then so we just have this queue, and then which is what I just said, like O of w or O of n, depending on how you want to look at it. And then we have this list, where the list is technically O of h, where h is the height of the tree, because we're only storing one node for each level in this list that we're returning. But that's always going to be less than O of w, because like as the tree gets taller, it's also going to get wider. So the O of w would like dominate, and then we just would simplify it down to this. So yeah, that's kind of it for this problem. I hope that made sense. Thank you guys for watching, and let me know what problem I should do next. Bye.